Seismic behavior of HSC eccentric beam column connections. Abstract analytically studied of 6 full-scale high-strength reinforced concrete, HSC with equals 75 MPa, and normal strength reinforced concrete, NSC with equals 25 MPa, eccentric beam column connections under seismic loading have been carried using the finite element computer software ANSYS. The applicability of the joint shear force provisions used by international codes, e.g., the American Concrete Institute, ACI 318-14, the New Zealand Code, NCS 2006, and the Eurocode 2, EC2, are examined when applied to HSC eccentric beam column connections. The main investigated parameters are concrete strength and a beam's eccentricity relative to the column. The ultimate failure load of connection with beam side at the column edge is less than that of the reference connection, without beam eccentricity, by about 55% for connections constructed from NSC, while the ultimate failure load reduced by about 25% for the same connections constructed from HSC. The calculated joint shear force using the ACI 318-14 equations is conservative for NSC and more conservative for HSC eccentric beam column connections. The joint shear force predicted using the equations of NCS 2006 is more conservative for both NSC and HSC eccentric beam column connections. On the opposite, the situation is reversed for HSC when the EC2 is applied. Though the ACI 318-14 limits the eccentricity between the beam and the column center lines to 1/8 of column width, it has been found that the eccentricity of 15% of the column width is still on the safe side as predicted the ACI 318-14 for HSC connections. Keywords: reinforced concrete, seismic response, nonlinear analysis, failure, joint shear strength. 1. Introduction. In most cases of construction beam column connections it is often required to construct eccentric beam relative to column. This eccentricity between the beam and column contributes to the creation of torsion in the contact region parallel to the exterior edge of the structure under lateral loading. This torsion in the joint creates extra shear stress and can adversely affect the joint's inelastic behavior. Most studies are devoted to the seismic behavior of reinforced concrete beam column joints, constructed from NSC with compressive strength less than 40 MPa. With widespread use of HSC with compressive strength approaching 140 MPa, studying the seismic behavior of the HSC eccentric beam column connections has become necessary. Present design guidelines too are focused on limited experimental work on eccentric connections and take into account post-earthquake observations 5 of increased damage to external connections between the beam and the column center lines. Previous 27 indicated that beam eccentricity leads to unsymmetric damage in the joint due to additional shear stresses caused by torsion. This damage resulted in pinch load versus drift hysteresis curves for the subassemblies and low energy dissipation capacities. Consequently, in the recommendations of the ACI Committee 352, the shear strength of the eccentric beam column connections is decreased by using a smaller effective joint width if the eccentricity of the beam to column centroid exceeds 1/8 of the column width. The investigation's main objective is to research the seismic behavior of both NSC and HSC eccentric exterior beam column connections and draw an analogy between both types of connections. The finite element method is utilized via the software ANSYS to expand this analysis. The applicability of the provisions on joint shear force used by international codes, e.g., the American Concrete Institute 4, the New Zealand Code 22 and the Eurocode 211 are investigated when applying to HSC eccentric beam column connections. 2 codes provisions. 2.1 ACI 318-14. The joint shear design force across a connection shall be taken as follows. 4 connections confined to all 4 faces by beams, 1. 4 connections confined to 3 faces by beams, 2. 4 other cases, 3. Where is the cylinder compressive strength of the concrete, is the effective cross-sectional area within a connection, is the effective joint width, is the beam width, is the column depth and is the smaller distance from beam edge to column side. 4 finite element analysis. 4.1 validation of the model. With the comparison of the experimental program 14 and analytical results, the validation of the current model it has achieved of the range of 91 to 93% as shown in Fig 3, this disparity in results due to the effect of the boundaries conditions and assuming of the full bond between reinforcement and concrete. 4.2 finite element modeling. 3D nonlinear finite element analysis using the software ANSYS 3 has been performed to study the performance of eccentric beam column connections with normal strength concrete with equals 25 MPa and high strength concrete with equals 75 MPa. The concrete was modeled with solid element SOLID65. This element has 8 nodes and has 3 degrees of freedom for each node, nodal translations in X, Y, and Z directions. The bars were modeled with a series of 2 node link elements link 180. At each node this element has 3 degrees of freedom. Cf. 4.3 reinforcement. The 1 bar area of longitudinal beam and column reinforcement is 201.00 mm2. The modulus of elasticity was defined as 2*10⁵ MPa and the Poisson's ratio was taken equal to 0.30. The yield strength of longitudinal and transverse reinforcement was equal to 360 MPa and 280 MPa, sequentially. A perfect bond was expected between rebar and concrete. SE. 4.4 concrete. The elasticity modulus of concrete was calculated according to the ACI 318-14 formula which gave values of 23,500.0 MPa and 35,652.04 MPa, for concrete with equal to 25 MPa, and 75 MPa, sequentially. Cf. 4.5 The finite element mesh. In order to obtain accurate results all elements have the same mesh size. The type of mesh selected in the model is hex/wedge. The concrete solid element SOLID65 is the mesh element for concrete and its size 50 mm*50 mm*50 mm. The link element link 180 is the mesh element for rebar with mesh 50 mm. Fig 4 shows concrete volume meshes for reference exterior beam column connection. 4.6 Boundary condition and load history. Loading and boundary conditions were performed in the model of exterior beam column connections to simulate the experimental test setup 14 as shown in Fig 4. The base of the lower column was hinged and the top of the upper column was roller. The right edge of the beam was loaded by reverse loading as shown in Fig 5 to simulate the beam column connections under earthquake loading. 1230.0 = 5 Analysis of results. 5.1 Crack pattern. All beams failed with the crack patterns shown in Fig 6, A, to Fig 6, F. As presented in Table 1, the initial crack of reference connection EBCN1, the center lines of the beam and column are coincide, was observed at a load of approximately 40% of the failure load. Most cracks seemed first at a distance 50 mm from the column face also extend to the beam edge. For connections EBCN2, eccentricity equal to 60 mm between the center lines of the beam and column, i.e. 15% of column depth, and EBCN3, the beam side at the column edge, the initial crack was observed at a load value of approximately 55% and 53%, respectively. Most cracks appeared for connections EBCN2 and EBCN3 first at the column face and not extend to the column edge. The crack pattern of all studied HSC exterior beam column connections was analogous to this of NSC connections. For connections EBCH1, EBCH2, and EBCH3, the initial crack was observed at a load of approximately 39 to 45% of the failure load. Though the ACI 318-14 limits the eccentricity between the beam and the column centerlines to 1/8 of column width, it has been found that the eccentricity of 15% of the column width is still on the safe side as predicted the ACI 318-14 for HSC connections. These results indicate that the cracks were initiated in the exterior beam column connections from NSC at loads lower than those of that from HSC, 50 to 75%. 5.2 Ultimate strength. The ultimate failure load is affected by concrete strength and beam eccentricity as observed from the results in Table 1, the maximum equivalent bond misses for all studied beam column connections as shown in Fig 7a to Fig 7f. For NSC connections, the ultimate failure load of connections EBCN2 and EBCN3 is smaller than that of the connection EBCN1. The center lines of the beam and column are coincide, by approximately 54% and 55%, sequentially. For HSC connections, the ultimate failure load of connections EBCH2 and EBCH3 is smaller than that of the connection EBCH1. The center lines of the beam and column are coincide, by approximately 5% and 25%, sequentially. It became clear that use high-strength concrete greatly enhanced the overall performance of the eccentric connection and delayed degradation of joint shear stiffness and strength. These results indicate that increasing the concrete strength from NSC with equals 25 MPa to HSC with equals 75 MPa led to a clear rise in the ultimate failure load of the connections with the center lines of the beam and column are coincide by approximately 29%, by 165% for connections that the distance between the center lines of the beam and column equal to 60 mm, i.e. 15% of column depth, by 116% for connections with the beam side at the column edge. Also the results indicate that, when using NSC, the effect of the distance between center lines of the beam and column on the ultimate failure load is clear on the opposite side when using HSC. Also, though the ACI 318-14 limits the eccentricity between the beam and the column center lines to 1/8 of column width, it has been found that the eccentricity of 15% of the column width is still on the safe side as predicted the ACI 318-14 for HSC connections. Cf. 5.3 Reinforcement strains. Fig 8a to Fig 8f indicate the rebar strains in the beam's upper and lower longitudinal reinforcement. It has been noted, for NSC beam column connections the strains in the longitudinal beam reinforcement don't reach to yielding. On the other hand, the situation is reversed for HSC beam column connections. For HSC connections, the load-producing first steel yielding connections EBCH2 and EBCH3 is smaller than that of the reference connection EBCN1 by approximately 8% and 27%, sequentially. In the case of NSC connections, the initial crack load is lower than that of similar HSC connections, around 50 to 75%. Also, it has been noticed that the strain distributions for all HSC beam column connections are similar. 5.4 Hysteretic lateral vertical loading curves versus beam edge displacement. Fig 9a to Fig 9f show the hysteretic lateral vertical loading curves versus edge beam displacement for all the studied connections. Table 1 gives the lateral load peak values immediately before failure with the vertical displacement at the beam edge. The maximum displacement at the beam edge for connections EBCN2 and EBCN3 is smaller than that of the reference connection EBCN1 by approximately 64% and 65%, sequentially. Whereas, the maximum vertical displacement at the beam edge for EBCH2 and EBCH3 is smaller than that of the corresponding reference connection EBCH1 by approximately 36% and 70%, sequentially. From the above results, the maximum vertical displacement at the beam edge of the HSC connections is larger than that of the connections from NSC by about 73 to 95%. 6. Comparison of results with codes provisions. The envelopes of the analytical joint shear forces of the studied connections are compared with that calculated from studied international codes as shown in Table 2. This contrast illustrates the joint shear force estimated utilizing the ACI 318-14 equations is conservative for NSC and more conservative for HSC eccentric beam column connections. The joint shear predicted using the equations of ANSYS 2006 is more conservative for both NSC and HSC eccentric beam column connections. By contrast, the situation is reversed for HSC when the EC2 is applied. 5 Conclusions. The following can be understood from the findings of this analytical investigation. 1. For NSC connections, the ultimate failure load of connection that the distance between the center lines of the beam and column equal to 15% of column depth is less than that of the reference connection by about 54%, while the ultimate failure load reduced by about 5% for the same HSC connections. 2. For NSC connections, the ultimate failure load of connection for beam side at the column edge is less than that of the reference connection by about 55%, while the ultimate failure load reduced by about 25% for the same HSC connections. 3. The joint shear force estimated utilizing the ACI 318-14 equations is conservative for NSC and more conservative for HSC eccentric beam column connections. 4. The joint shear predicted using the equations of ANSYS 2006 is more conservative for both NSC and HSC eccentric beam column connections. By contrast, the situation is reversed for HSC when the EC2 is applied. 5. When using NSC, the effect of the distance between center lines of the beam and column on the ultimate failure load is clear on the opposite side when using HSC. 6. Though the ACI 318-14 limits the eccentricity between the beam and the column center lines to 1/8 of column width, it has been found that the eccentricity of 15% of the column width is still on the safe side as predicted the ACI 318-14 for HSC connections.